Okay, welcome back to part two. Continuing talking about how derivatives affect the shape of a graph and looking at the different derivative tests. Before we move on, we need to talk about a new phrase, a new idea, a new word, something about the word concavity, dealing with the concavity. And concavity talks about the shape of a graph. Okay, so the definition. If the graph of a function f lies above all of its tangents, on some interval, then, so if the graph of a function lies above all of its tangents on some interval, then it is called concave up on that interval. If the graph of f lies below, and we're going to do graphs of this. We're going to look at it. We'll pull it apart. We'll take a look at this. If the graph of the function f lies below all of its tangents on some interval, then it is called concave down on that interval. Let's take a look at just two quick little graphs. Let's look at this graphically speaking here. So in the first graph, suppose I've got some sort of function that looks like this. Over some interval from A to B. And if I take a closer look, I notice that I've got a minimum value here, but I want to focus in on all of the tangent lines. And if I take a look at the tangent lines, I've got a tangent line here, and 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 a tangent line here. And notice that the function lies above all of its tangent lines. So this function would be concave up over this interval because the tangent lines are below. The function is above all of the tangent lines. Similarly, if I had another function like this, and I look at all of the tangent lines, this is my function. We'll call it g of x over some interval from a to b. And the tangent lines, I've got a tangent line right here. It looks like I've got a maximum here, a tangent line right here. I've got a tangent line right there, a tangent line right there. I've got all of the tangent lines. Now notice that the function lies below all of its tangent lines. The tangent lines are above. So this function is concave down. So concave up and concave down. And they can start and end at the same places. I could have a function that's like this, concave down, or I could have the function like this that would be concave up. And it starts at the end of the same places. It's got the same slope with the secant line from the beginning to the ending. But concavity really tells me a lot. And concavity is actually going to be, as we'll see in a moment, a second derivative test. But before we do that, I want to take a closer look at a graph. Now, here's the graph. Let me pause for a moment. I want you to copy down this graph as best as you can. And what we're going to do is we're going to answer the questions on this graph. Where is it concave up and where is it concave down? I notice that I've got endpoints of A and I. Notice that it is continuous through its entire domain from A to I. It looks like I got a couple of corners and cusps. It looks like I've got some absolute maxes and maybe some absolute mins, definitely some local maxes and local mins. But again, I'm concerned with the concavity here. It's all about the tangent lines. All right, so if you need to pause the lesson at this point to kind of pause the video to make sure you've got this copied down, because I'm going to move on here. And I want to look at the concavity. So if I start here at A, and I'm going to use, again, my protractor here, and I'm going to look at the tangent lines. And it looks like the tangent lines are above, 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 above. And if the tangent lines are above, that means it's concave down. Here, it's still concave down, still concave down, concave down. It looks like right around here at point C, it changes. Now, all of a sudden, the tangent lines are below. So, it looks like from point A to C, it is all concave down. At C, all of a sudden, the tangent lines are below. So now if the tangent lines are below at C, below, 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 they're still below here at D, below, below, below. It looks like something is changing right around here. Oh, I didn't give that a point. I should have labeled that a point. I'm definitely having a change in my concavity somewhere right around here. We'll call this point S-C-H-I-J. It looks like that from C to J, it's concave up. And now my tangent lines after point J, now my tangent lines are above again, so concave down, concave down, concave down, concave down. Certainly something strange is happening at E, but is my concavity changing here? If I go to my tangent lines, now the tangent lines are below, so yes, the concavity changed here at E. So it looks like between these 2 points, it's concave down. From J to E, concave down. Now what's happening? From E, my tangent lines are below, 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 or I should say the function is above, 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 above. At point F, at that local minimum, the tangent lines are still above, 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 until I get to point G. And then is something happening here at point G? Now all of a sudden the tangent lines are below. Yes, the concavity has changed. So from E to G, it's concave up. The tangent lines are below, below, below. And then all of a sudden after 8, the tangent lines are going to be above and above, above. So from G to H, it's going to be concave down. And then after this, the tangent lines are above. Let's see, did I get that last part? Concave. The tangent lines are above. The tangent lines are above, above, above. Oh, you know what? I think this should still be concave up, shouldn't it? Look at the tangent lines. If I put a tangent line there, the function is below, the tangent lines are all above. This should be concave up here as well over this interval. This should be concave up as well. All the way from E to H is all concave up. Here, the tangent lines are below. It definitely changed. So to I, this is going to be concave down. And we actually have a special test, a concavity test. Let's take a look at it. So the concavity test is actually a second derivative test. And here's what the concavity test says. First, if the second derivative of the function is positive for all x in some interval, then the original function is going to be concave up. On that interval. If the second derivative is less than 0 for all x in over some interval, then the original function is going to be concave down on that interval. So that's my concavity test. The other thing that's interesting is happening is where the concavity changes, where I change from concave up to concave down, those points on the last graph where the concavity changes. They are not maximum or minimum points. We have a special name for that. So the point where the concavity changes is called an inflection point. So if I change from concave up to concave down, or from concave down to concave up at some point, that point is called an inflection point. All right, so what I'd like to do now is I want to look at a graph, and I'm going to ask you a bunch of questions about this graph. So here we go again. Here's the graph. Again, if you want to pause the video and copy down this graph, and I'm going to ask you a bunch of questions about this graph and about the concavity in dealing with this. This graph is actually a graph of my original function, f of x. It's not the derivative or the second derivative. It's an actual function. This is the kind of thing where I would put this on the board, and we would spend a lot of time kind of discussing this and going over it and talking about it, especially if you get some of the answers wrong. And I've got a bunch of true or false questions that I want to ask you about this graph. All right, so here come the true or false questions. So looking at this graph, I want to know, are these questions true or false? So I'm going to pause actually for a moment. You don't have to stop the video. I'm going to pause for a minute and give you a chance to copy this down. Oh, it's not really curvy there. It should be nice and well-behaved and curvy. I'm not trying to be super tricky. I just noticed that it doesn't look really good right there, does it? Just makes that a nice little well-behaved curve. And I want to talk about, are these statements true or false? So I'm going to give you a minute, copy it down, look at it, think about it. I'll give you 30 seconds or so. I'll tell you when I'm ready to start answering them, and if you're not ready to go over it yet, hit pause on the video. While you're copying it down, I wonder what the weather's like. How you guys doing at school? Anything exciting going on? I really miss being at school. I honestly, I really do. I'm not having as much fun doing these videos as interacting with you and talking. So I really don't enjoy this as much. This is not the way I would like to ever really teach in the future. All right, right, I'm going to go ahead and answer these questions now. So if you're not ready, hit pause on the video and spend a little bit more time, but not too much time because we still need to get through more things on this. So go ahead and hit pause. Got another 5 seconds before I start answering these questions. 5, 4, 3, 2, 1. All right, here we go. So first question, is the second derivative positive for all x's over the interval from 2 to 4? So from 2 to 4, is the second derivative positive? In other words, is it concave up? Are all of my tangent lines below? Yes, then this would be true. How about this one? Is the second derivative negative for all x's over the interval from -4 to -2? Here's -4 to -2, and it looks like the tangent lines are below, but then at some point they're above and above and above. It looks like they change right around there, right around -3 as they change, so it's not the same over the whole interval. This is going to be false. Is the second derivative at 6 equal to 0? The second derivative at 6? Well, if I take a look at this, the first derivative certainly would be 0, wouldn't it? The slope of my tangent line would be 0. But is the second derivative going to be 0? No. Why not? Because there's no concave down. So this would be false. The next one, would the second derivative at 2 be greater than 0? So at 2, my second derivative, here it is. Clearly the first derivative would be 0. And notice that it's negative down here. So would the second derivative be greater than 0? Would it be positive? Yes, this would be true because of the concavity. And then finally, number 5. F is concave up in the interval from 0 to 2, concave up. And again, if I put all of the tangent lines there, all of the tangent lines would be below, the function lines would be above, so this would be true. There's all my answers. All right, let's take a look at a couple of more graphs and then talk about the very formal second derivative test. So I'd like to introduce the second derivative test by looking at 3 graphs. In the first graph, I'm just going to have something that looks like that. In the second graph, I'm going to have something that looks like that. And in the third graph, I'm going to have something that looks like that. And what can I tell about these things, about these different functions? These are all functions. What can I tell about the first derivative and the second derivative? Well, here, the first derivative, the tangent lines would all be negatively sloped. Here, the first derivative, all of the tangent lines would be positively sloped. Here, the first derivative, let's see, positive, 0, positive, would all be greater than or equal to 0. They would all be positively sloped there. Maybe I've got a 0 tangent here, maybe not, I don't know. But certainly, I would not have any negatively sloped tangent lines there. What about the second derivative? Well, the second derivative, all of the tangent lines are below, so it's concave up, which means the second derivative would be less than 0. How about here? Well, here, all of the tangent lines are above, so this would be concave down. The second derivative would be less than 0. Oh wait, this should be greater than 0, shouldn't it? Shouldn't that be greater than 0? And here, notice that at some point it changes. So my second derivative is going to be less than 0 when x's are less than a, and my second derivative will be greater than 0 when x's are greater than a. All right, so now let's be a little bit more formal, and let's talk about the second derivative test. This is the second derivative test. In other words, my f double prime. All right, the second derivative test tells me this, that if the first derivative at some point c is equal to 0, and the second derivative at c is positive, then what's happening? I have a minimum at f of c. If the first derivative at some point c is equal to 0, again, if the first derivative is 0, we know it's a tangent, a horizontal tangent. I've got a maximum or minimum point here. And the second derivative is less than 0, then I know it's going to be a maximum at f of c. I know I'm going to have a maximum value there at c. All right, so let's try to put this together now. I've got a kind of an awkward, difficult little activity that I want us to do. This is another one that in class we would certainly struggle with and spend a lot of time with. I want to sketch a graph that has all of the following things true. So sketch a graph where the first derivative at -1 is 0, that the first derivative of 0, or the first derivative at 1 does not exist. So the first derivative of -1 is 0. The first derivative at 1 doesn't exist. The first derivative of the function is, let's say that it is less than 0 if the absolute value of x is less than 1, so from -1 to +1. How about the first derivative is greater than 0 if the absolute value of x is greater than 1, and the f of -1 is 4, and f of 1 is 0, and the second derivative of x is less than 0 if x is not equal to 1. So I want to sketch a graph with all of those things that are true at the same time. So again, let's kind of go over these things. The first derivative at -1 is 0. The first derivative at 1 does not exist. Something's happened there, makes it doesn't exist. The first derivative is less than 0 if x's are between -1 and +1. The first derivative is greater than 0 if x's are greater than 1. Absolute value of x is greater than 1, so on either side of 1 and -1. That f of -1 is 4, f of 1 is 0, and the second derivative of x is less than 0 if x is not equal to 1. Now, you might want to pause the video here, write all this down, and try drawing a sketch of this. There's more than one possible answer here. I'm going to give you one possible answer. So go ahead and hit pause on the video and look at this, try this, kind of help each other out. Don't spend more than like 5 minutes on this, and then I'll give you the answer. All right, so get ready. I'm going to go ahead and do the answer here in a moment. So go ahead and hit video if you're not, hit pause if you're not ready. All right, here comes the answer. Or I should say, one possible answer. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. All right, let's deal with a couple of those important points that we can't seem to fix. I know I need to have that point right there, and -1. I know I need to have that point right there. I need to have, I think there needs to be a straight line between these 2 points, and then after that I'm going to have some sort of curvy bit here, and then over here it's also going to have to be, for the second derivative, it's going to have to be concave down, so something like that. All right, so there's one possible answer, and there's really not much variety to that. We're pretty much stuck with those things right there. But this is the kind of thing, we've seen this before. AP loves this. Sketch a graph with the following things. It was on one of the last tests. And as we add these new different tests, first derivative test, second derivative test, the idea of concavity, concave up and concave down, and sketching, should this look like this or like that? And this part right here, should it go this way or should it go that way? It's all about the concavity. So just being able to read the second derivative tests and know the concavity here, that it had to be concave down on either side of 1 and -1. All right, that ends this video. Kind of a long one, a lot of stuff going on here. The homework is kind of tough, 4.3. There's a lot going on in there. Look over all of the tests, look over the examples. The textbook uses different examples than I have. I haven't just done all the same examples that are in the textbook. And then tomorrow we're going to move on to something a little bit more interesting. We're going to switch gears and get away from graphs for a moment and kind of go back to some of the foundations of working with derivatives. And I'll talk to you again soon. Bye-bye.